Hi everyone, welcome back. So in this video, I'm going to show you how to analyze a non-inverting summing amplifier or op-amp. Now in the previous video, I did an inverting summing op-amp. The analysis for that one is going to be, well, it's actually a lot easier than this one. Now there are several ways of doing it, but before we go into it, let me just remind you guys of the ideal op-amp assumptions that we're making whenever we're analyzing an op-amp circuit. So number one is because of the infinite input impedance, there won't be any current flowing into both terminals. So that's I1 and I2 will both be 0 amps. And because it's 0 amps, that means there won't be any current through the internal impedance, which means there won't be a voltage drop, which means whatever V2 is going to be what V1 will be. So whatever V1 is going to be, V1 and V2 will just track each other basically. All right, so let's, first of all, as usual, let's label all our currents and voltages so that we can make sense of the equations that we're making. So first, I'm going to label the feedback current. All right, so the feedback current is going to be going that way, all right, going from right to left through RF. Okay, so it's going to go through RF like so. And again, because when it gets to this node, this junction, all of IF will end up going through Rn, and none will go into the inverting terminal. All right. So therefore, IF will just simply appear across Rn. Okay. Okay. So now, in terms of some other currents, if we look on the bottom side here, where we have V1 and V2. Again, because no currents will be flowing into the non-inverting terminal, so if I have a current, if I define a current I1 that flows through R1 like so, all right. So if a current is going from left to right of R1, then none of that current will go into the non-inverting amplifier. In fact, all of them will just come back out to V2, right? So all that current that goes in will just come out exactly as it went in. All right. Okay, so I1 would be equal to I2. All right, we'll write that equation in a bit. In terms of voltages, we have, of course, the if I want to look at R1, sorry, RF. So if you have current going from right to left, so therefore the voltage is going to be positive from will be pointing towards the right of RF, right? So it'll be positive to the right. Okay. Similarly for Rn, it will be positive again going to the right because the current is flowing from right to left. So therefore, VRn, the voltage across Rn, will be positive on the right hand side. All right. Okay, and then the voltage across R1, since current is flowing from left to right, so then the voltage will be positive, pointing towards the left, meaning that the higher potential will be on the left side of R1. And similarly for R2, since current is flowing from right to left, therefore the voltage across R2 will be positive from the right compared to the left. Okay. Now, I'm going to label these nodes as well. So if I were to call this node VP, P for plus, actually. So if this node is labeled as VP, this entire node is labeled as VP, then by the second assumption, the upper node is also VP. All right. So we have a VP on this side, and we also have a VP on the inverting node. All right. Okay, so I think we can start writing some equations. So the first one I want to write is about VP. So my idea is I want to write an equation for VP that is related to the circuit connected to the non-inverting side, and then I'm going to write another equation for VP that's related to the circuit connected to the inverting side. All right, and then I will equate the two, and I'll try to solve the equation. All right. So so voltage node, node on the non-inverting terminal. All right. Now on the non-inverting terminal, I can write an equation that says I1 is equal to I2, right? So because no current from I1 will end up going into the non-inverting terminal. So I1, so I can say that I1 is equal to I2, right? So I could say I1 equal to I2. So let's put that down. I1 is going to be equal to I2. All right, so that's just KCL. All right, so I1 equals to I2. What else can we say? Well, we can actually write a full equation here. So let's just talk about I1 and I2. So let's talk about I1 first of all. All right. So current through R1. All right. So that is called I1. So I1 is through Ohm's law. All right. So I equals V over R, the voltage divided by the resistance. So the left side of R1 is labeled as V1. So that's what that is, V1, minus the right side of R1 here. That's VR1, right? So that's VP. So we label that as VP. All divided by R1. All right? So that's our current through R1. And similarly, current through R2. That's basically I2. All right? Well, if you look at I2, V over R again. So the voltage is on the right-hand side. All right, so the voltage is on the right-hand side. So therefore, it's going to be VP minus V2, right? Because V2 is on the left side, all right? Divided by R2, all right? So that's those are the two equations that we found for I1 and I2. Now, given the fact that they need to be equal, so let's just do that next. All right, so let's just do that next. So basically, let me just rewrite that equation again. So I'll just say, oh, sorry. So I1 is equal to I2. All right. Since I1 is equal to I2, so now I can write an equation that puts the two together. So I can say that this part here, right, is equal to that part there. All right. So that's that part is equal to this. All right. Okay. So now let's have a look at converting. I mean, basically, let's change this so that we have it in the form of VP equals something. All right, which we can then compare with the equation that's at the upper node. All right. Okay, so let me just bring that down. Okay, so that's going to be so what I'm going to split this up first. All right, so I'm going to split that up into its own fractions. So that's V1 divided by R1. All right, minus VP divided by R1. So I'm just expanding the term. So equals to VP over R2. All right, minus V2 over R2. Okay. So now we bring the VPs together. So let's bring the VPs together. So then we have a negative VP over R1. All right, and so this other VP divided by R2 we put to the left, so it becomes a minus VP over R2. Okay, So that's going to be, all of that on the left will be equal to everything on the right. So here, I'm just moving V1 over R1 to the right-hand side. So you're going to get, well, first of all, you have that V2, the original V2 divided by R2. I think I'll put my minus V1 first. Okay, V1 divided by R1. All right, minus this. Okay. Okay. So that's our equation. So then we can factorize VP. So then what we'll have it. Oh well. First, I think first thing we want to do is actually maybe convert everything into positive by multiplying both sides by -1. All right. So then I will factorize VP. So I'm going to have VP. That's going to be, and inside the bracket will be 1 over R1. Sorry, R1. Plus now, right? Because we have converted everything by multiplying both sides with -1, so everything becomes positive. All right. All right. That is equal to. Again, this side will all be positive now because we've also multiplied this side by -1 plus V2 divided by R2. All right. Okay. Okay. Sorry. I think this part became a subscript. I need to just shift this up. Like so. All right. Okay, so now I can put VP all by itself on the left side. All right. So therefore VP is going to equal to, okay, what is it? Well, it's going to be this whole thing multiplied by this whole thing, right? Now, if you notice, 1 over R1 plus 1 over R2, when I go to the other side, becomes 1 over all of this. And hopefully you actually remember that it's actually the equation for a parallel to a pair of parallel resistors of R1 and R2 if I move it to the other side. Okay, maybe I'll just make it a little bit more obvious here. So I'll just say like this. I won't change anything. So it's very obvious that is actually a parallel. That's the parallel equation for two resistors. All right, so like that, and then the whole thing closes. All right, and then multiply by this entire, well, the rest of the expression here. Okay. All right. So now, so this is the expression that we have. So as you can see, this term here is simply basically the parallel of two resistors, R1 and R2. Right. That's the expression for parallel resistors. So what I'm going to do now, I'm just going to maybe just make it a little bit obvious that that's what it means. All right. So I'm going to change this into a VP is therefore equals to R1 parallel with R2. Okay. Then multiply by the rest. Okay. Okay, so that's our expression on the right hand side, on the bottom circuit. This bottom circuit is equal to all of this. All right, so now let's have a look at what about on the top side. Well, if you look at the current IF, since IF actually flows through RF and then through RN, remember, yeah, it doesn't go through the inverting terminal because no current will go through there because of the infinite input impedance, right? So effectively, RF and RN are actually in series, right? Because the same amount of current are flowing through both. So since they are in series, and then I have a VP here and a VO at the top, okay, on the right, but at the top of, if you like, these two resistors, they effectively become a voltage divider. So so I can write voltage divider at the inverting terminal. All right, so I can write an expression for that. So that means it's going to be VP is going to be equal to VO, which is the overall voltage across both resistors, right? Multiplied by Rn divided by Rn plus Rf, right? So that's our standard, if you like, voltage divider expression. Okay. All right. So now we actually have both a VP terms for both left and right. So now we can actually combine these two uh, and form an equation that will just simply have VO on one side of the equation. All right. So let's do that. So if I say combining, or sorry, not combining, equating the two VP expressions. All right. So then what I'm going to have is an equation that is like this. So I'm going to put this one first. So I'm going to put this one on the left. All right. Put that one on the left. Is going to be equal to all of these, which are will be on the right of my new equation. All right. So equals to all of that. All right. Okay. So now I just need to put Rn over Rn plus Rf across to the other side to finally form what VO should be. So VO, all right, is going to be equal to. Okay, so what I'm gonna do is I'm gonna put this term here right in front of the first multiplication factor. So obviously this is multiply. So when it gets on the other side, it's a divide. So the two actually top and bottom will actually flip. So you're gonna have an expression like this. Divided by Rn. Okay, and then the rest would be whatever we have here. All right, whatever we have here, that's what it's going to be. All right. Okay, so again, I can further simplify that by noting that I can do an Rn over Rn plus Rf over Rn there. So therefore, my final expression is going to look like this. Okay, and then the rest is just these factors again. Okay. Okay, so it's a bit more complicated than obviously the inverting summing op-amp. But hopefully you can see that what happens if let's say all the resistors are all of the same value. All right. So when all the resistors are of the same value, then you're going to get a 1 plus 2 here. All right. You're going to get 1 plus 2 here because they're both going to be R over R, so it's going to be 1 plus 2. Sorry, 1 plus 1. So the whole thing is going to be simply 2. All right, and then you also have this R1 parallel with R2. If you remember, R1 parallel with R2, what we do is we'll multiply the two terms divided by the addition of the two terms. All right. So let's just look at one scenario. So for example, what we have right now, this is, for example, is the full expression for what VO is. Okay, so let's just look at an example of what happens if we now let me just bring that down a bit. All right. So what happens when we have a certain situation, certain scenario? So if I'll just show you one example. All right. So if we have everything to be the same, that means we have Rf is equal to Rn is equal to R1 is equal to R2, and all of this is equal to R. All right. So if we have such a condition, then our equation at the top here, we can simplify. It's going to get simplified to what? Well, VO is going to equal to, well, in bracket will be 1 plus 1, right? That's what's in bracket is going to be. And for R1 times R2, let me just remind you guys what happens to R1 plus R2. Sorry, R1 parallel with R2. That's basically R times R divided by R plus R. All right, so R times R divided by R plus R. So you're going to get, it'll be R over 2. All right, it'll be r over 2. So r times r is r squared divided by r plus r, which is 2r. So r squared over 2r, the r's will cancel out, leaving just one r at the top and number 2 at the bottom. All right, that's what that's going to be. All right, and then equally for v1 over r1 plus v2 over r2, since r1 and r2 are both equals to r, I can factor that out. I can factorize that out. So which means it's going to be 1 over r, right? And then multiply by what's left, which is v1 plus v2. All right? Okay? So that's what's going to happen. Well, obviously you can see some further simplification here. 1 plus 1 is 2. This r and that r will cancel out, right? So that will cancel out. Okay, I think I'll use a different color here for the answer. Okay, so this r and that r will cancel out, the bottom r here. That will cancel out. Okay, so they will cancel out. And the 1 plus 1 and the 2 will also cancel out because 1 plus 1 is 2. So that will cancel out with this 2, the one at the bottom here. If I can highlight it. All right, so yeah, so that's also gone. So what's left is basically just v1 plus v2. All right. So once you have all the resistors become the same, then our expression for VO simply becomes V1 plus V2. So this is a, if you like, non-inverting sum. You don't get a negative term. I mean, basically, a negative term simply implies that the output waveform would be out of phase, 180 degrees out of phase with the input waveform. All right. In this case, it won't be so. All right. So that's an example of what happens when we make certain assumptions about the various resistor values. Now, if there were more than these two resistors, let's say there's R3, R4, up to Rn, the general expression will basically be the parallel of all those resistors, all right? And then the rest will be V1 over R1 plus V2 over R2 plus V, and so on until Vn over Rn, okay? And that will be it. That will be the general expression for a non-inverting summing amplifier. All right. So okay. So that's about it. And I'll see you guys next time.